Right, okay, so I think we are back online, and we were originally looking at this in the last video, looking at this Euler method, and we built like some version of this method, um, and it's the explicit Euler formula, which basically, given a given a position or like a value, we can work out the next value. So we sort of like given this value here, this S of J of T is here. So given this and this time step and knowing the slope in terms of its unit of time, so the rate of change of this value with respect to time, so if you know its first derivative basically, you can compute the value at the t plus 1, the next interval. So that's basically what was done, and we mentioned that t j plus 1 minus tj, which is one time step, is given that this we assign it like this equal spacing basically, and we call that h. And this other piece here is the actual slope basically, so that's that continuously differentiable function, and that's the original starting point. So those are kind of like the three parameters, and that's quite a common thing to be happening. And from that, you've got like effectively 0.1, and then sort of like 0.2, which is the time step. 0.1 is the starting point, 0.2 is the starting step, and 0.3 is the slope. And that's like the, sorry, not the starting, you've got the starting point, then you've got the time step or the gap in between on the x-axis, and then you've got the slope. So with those three things, you can get to the next time basically. So yeah, that's pretty much it. So that's what we got to. And here's sort of like the little diagram there. That's that h, which is the gap between tj plus 1 and tj. And then we'd need to know this slope. So, and this function here, this function over here is this, it's the slope basically, some continuously differentiable differentiable function, however one says it. And then it was this little method. So this is kind of like the recipe for what's done. And we copied this piece of code, it was just a copy basically, and we pasted that into our VS Code, which is over here. Had to do a couple of little tweaks. One thing is using the Seaborn styler to sort of like comment that out in Matplotlib. I never use that, but that's because I'm not using a Jupyter notebook. And the other piece was this lambda function. The linter didn't like the lambda function, so it sort of like said put it into a regular function, and I kind of like agree with the linter on that. I don't want to put things into. I'm not a fan of the lambda functions. I much rather prefer this. For me, it's much cleaner. So anyway, the linter does that. I wonder if like have done a video like. There you go. We could have it in one line if you really felt you wanted a one line thing. But anyway, that's kind of like where we were. And what else was there in there? So this did a plot.show, and actually I was just running through this because like I've got the hints automatically turned on, these code suggestions from Copilot. I've used 3% of my Copilot, yeah. And just as I was going, it's got like some error analysis. So that's kind of like a freebie. And like every time you just keep hitting return, and the Copilot automatically sort of like preempts the guess of the next line and so forth. And like I didn't write any of this extra piece of code. It does some error analysis. Now I want to put this all into one function basically. I think that's the thing that I need to be doing. So in order to be doing that, yeah, anyway, when I hit run, so I have actually like committed this, but when I do hit run, it's going to, it launches this, and then it's got this approximate solution, and that's what we got to at the end of the video. So like that's our approximate solution with the blue dotted line, the blue dots and the dashed lines in between, and the green one's the exact solution. And actually, if I close this, the next one will pop up, which is this piece over here, and that's the error. So it's quite nice, it's quite cute. This piece over here, it's all like computes the error. So that's the exact value. And then this is effectively an array. This is a result of the exact values, which is the NP exact times minus the computed values, which is I guess this piece over here, that little array of S's. So it's just basically computing the errors between the exacts and the actuals. But one extra piece was, and that's it, we can see that the difference, or the biggest error, so the error is growing, by the way. It starts off at 0, so you got no error. And then it's sort of like a systemic error that keeps on building up. And it gets to like 0.3 at the end of it. And I guess the bit that I missed was, because I had to jump off, the bit that I missed was this piece here, because you can change the time step, and if you do change the time step, I guess it gets a lot closer. So that's our first version. And that time step, if we notice in the code, H is step size. I call it a time step. I shouldn't call it a time step because it could be any sort of dimensions. I'm just used to using time on the x-axis from physics, but it doesn't have to be. So we got H equals 0.1, and then we're going to change it to H equals 0.01. Now, we won't see much change in the error analysis piece at the bottom in terms of the shape because it's going to just rescale itself. But nonetheless, let's just try this out with H equals 0.01. But what we should do to be able to verify is we'll see the steps come a lot closer to each other. So I'll hit that, run, and it runs, and there we go. The exact is now, you can, like, if I was, I don't know if you can zoom in, but you can see the green line is, the blue dots are exactly on the green line. And likewise, I guess, the errors have just dropped by a factor of 10, but so this was 0.03, now it's 0.003. So although it's taken the same shape, so, and that was kind of the point of it. So I guess that's that bit done. So I'm sort of like satisfied with that bit. But I wanted to clean it up a little bit. Actually, that was the one piece that I did want to do. So yeah, let's have a little read down below, and then I think I'll go and tidy up the code. But the explicit Euler formula is called explicit because it only requires information at Tj to compute the state at Tj plus 1. That is, Sj plus 1 can be written explicitly in terms of values we have, i.e. Tj and S of Tj. The implicit Euler formula can be derived by taking the linear approximation of Sj, the linear approximation of St around T of j plus 1 and computing it at Tj. So we still got the same formula there. Let's see this. Is that right? Do we have the same formula? Let's just scroll up. This bit here, okay. This piece here, we've got this we've got this function T and S of T, and down below we've got this function of T and S of T, j plus 1. Okay, fine. This formula is peculiar because it requires that we know S of Tj plus 1 to compute S of Tj plus, right, okay, fine. Yeah, because it's sort of like using the slope at the next point to give the original slope. However, it happens that sometimes we can use this formula to approximate the solution to the initial value problems. Before we give details on how to solve these problems using the implicit Euler formula, we give another implicit formula called the trapezoidal formula, which is the average of the explicit and implicit Euler formulas. Okay, yeah, you can do that. which is take this step, the half step, use both of the slopes, add them up. Yeah, okay, fine. So it's sort of like, it's not even a half step. It's these two, the sum of the pair of the two divided by 2. That's going to be the average, and then multiplied by h. So that's what that's going to be. To illustrate how to solve these implicit schemes, consider again the pendulum equation, which has been reduced to the first order. So, okay. The x component multiplied by the vector. The y component is g over L, which is, I guess if this is talking about a pendulum, it's talking about, you know, this thing that sort of like swings around, sort of like swings, you know, that way, and then swings the other way, and the force is the minus g, which is gravity. So you've got a downwards force, which is g. Minus is because it's going downwards, and this piece here is the length of the pendulum. So L is kind of like this length of the pendulum, and the x-axis doesn't change. That's just, I guess, that's why that's going to be, is that a 1 or no? That's a 1. And that's it. The other components, the orthogonal components, are 0. So these two pieces here, they're going to be, here, undo twice. These two pieces here are 0 because we're only talking about an x component, which is the 1 over there, and the y component, which is the minus g over L. So yeah, that's going to be that. For this equation, we've got this. If we plug this expression into the explicit Euler formula, we get this following equation. Remember, I guess, like I should point out that S of t is basically, I guess it's going to be S at a point of x in t and S at a point y in t. So that's like a vector. And this is a matrix. So this bit will multiply by that, this bit will multiply by that, and that will generate you the x components. So you've got like 0 or 0 lots of Sx, plus 1 lot of Sy, like that. And then you've got the next piece, which is, if I use red for example, you've got that bit there and that bit there, they multiply, so you've got minus g over L. It's, ignore the really bad writing of the S of x component. So that's why this is only in the x, this one acts in the x, on the x component, and then you've got plus 0 of the S of y component. So obviously, like, we can cross out both of these 0 components, so that one can go and that one can go, and that's why you are left with, after doing all of the pieces that are done, you're left effectively with Sy, because 1 lot of, that is an S by the way, Sy, and then minus g over L of the S of like x bit, so like, and that's basically it. That's what this matrix actually means when operated on this S of t, and that's at given at, and that's at the point in time of t, basically. So that's its vector, kind of like at t, basically. So we've now got the x component, which is contingent on this s of y, and then the y component, which is contingent on minus g over L of s of x. So something like that, basically. And yeah, so I guess this should all be split out because it's a little bit like not visible, maybe, or not. I believe that that's an equation, and this one is another equation, and then this one here is a third equation, right? And that gives you, I guess you've got the s of t of j plus 1, so you've got this first piece here, and then you've got these other two s of t of j's over there, like that. And we can plug the same expression into the implicit Euler equation to get this, and into the trapezoidal formula to get the one below. Okay, fine. With some rearrangement, these equations become respectively, okay, fine, and this is the inverse of a matrix. These equations allow us to solve the initial value problem, since at each state s of tj we can compute the next state. I wonder, right, that's going to be something else, I believe. So numerical error in instability, that's going to be something else, so I'll leave that one to another video. But I'm going to go back now. I'm going to focus on the code, more on the code and less on the maths at this point, although I'm like sort of like intrigued by the maths because I have to remind myself of this piece. Because I'm wondering actually what it does. You're welcome to put it in the comments what it does. I'll put that hello in the comment. Because we know, oh, I see, I think you put this into the original large equation, so s of t of j plus 1 is equal to all of this, but we know that this piece here, basically, that is that, therefore this component is actually this. So like if I was to sort of like drag it and drop it, but I can't, you know, that would fit into here. And that would give you s of t of j plus 1. I guess, but that's that function that would go in there, but this is only that piece that we need to put in there. I guess this is known at this point, these two. It's interesting to see how that works actually, but yeah. So I'm going to move, well, I'll do the piece I don't get actually, I'm sure that these are three equations. Like, that's equation 1. Colour them in. Like, this here is an equation. Because this isn't all one equation. And this one here is like a final equation, right? That's the way that I'm looking at it. Or is it different? Because this being true, I mean, this piece here would match this piece over here. This piece here matches this piece over here. Then this piece here in this equation this piece here, the H component matches. But I'm just wondering if the rest of it, like how that goes in, because I would just have thought that that last piece, that this entire box here, was basically that last piece. So anyway, I'm going to jump over to the code bit, because what I wanted to do, Control minus, and we'll get rid of the thing on the side here. And yeah, I wanted to put it into a function, I guess. So if name equals main, this is my main guard idiom, and then I'll do a here. I'm just going to put a def main. It's doing its autocomplete stuff for me, but if I was going to do that, this would then all have to be in tab over there. I think that should be fine because I've got this function, of course, so that's all going to be fine. This has to be one function at the moment because this value here, S, is you know, these values here, the explicit Euler method is the np.zeros of length of t. And t is this np dot range over there, so fine. So this S here is a, well, it's showing you here it's an NDO, it's a tuple of integers. And S0 equals S at time equals 0 is S0, and S0 is -1. That's like an initial condition. I could actually muck around with the initial condition as well. But I thought like what I wanted to do was remove Plotly, remove Matplotlib and use Plotly for a start because it will look a bit nicer. So import plot right. So I'm going to do a little bit of a cheat. So I guess I don't know if it's right. How will I do? Let's get this up. So let's just do Plotly. There we go. Plotly graphing library B04. Examples, fundamentals. So sort of, let me just click on any one of these, I guess. Right. I'll try that. Actually, let's just jump onto our friend. So, which is Gemini. Close all that. New Gemini. And then that's using Plotly Express. But this piece here was Plotly graph objects. One is, I think Plotly Express is a simple one. I think that might be sufficient of our, right. Both Plotly Express and Plotly graph objects are excellent ways to use in Python. Quick exploratory plotting is Plotly Express. Complex graph plotting, Plotly graph objects. Starting a new project, and so forth. Okay, we'll just go with the Plotly Express then. I think I can get away with that. So this. But I need to pip install, so I'll have to, not over here, but over here. Plotly. Right. That should do it, maintain. Right, and here's a little example. I'm not sure if Plotly Express will be enough. Yeah, okay, fine. So we just go there, go over here, pip install Plotly. Bada bing, bada boom. Right. So it looks like that's done, I think. Easy, right, so I want to plot the chart in Plotly. That's kind of like what I want to do. I wonder if I have to do a restart, by the way. Let's just go over there and wonder if there's any other bits. Right. Control I. In fact, I will hit the save button, Control S, and then I'll do Control I, and I'll do change to Plotly. Okay, I didn't do very well. Okay. Close. Right. Wonder if I can get away with this. You can change map Plotly to Plotly using the graph object scope, which allows you to go, okay, fine. Right. Right, I wonder, no. I'm just going to take that and then do replace. let's see what that does. Okay, still using the graph objects. Okay, fine. It's got the same def, so basically plotly replacement. Okay, fine. It's made it nice and explicit, so I'm going to have to use this, which is the graph objects. Okay, and then this function here is going to stay exactly the same. This parameter is going to stay the same, and here it's got this S0 is -1 explicit Euler method, so it's got S underscore approximate, and S underscore approximate of 0 is S0. So it's changed the naming thing, but I think that's going to be a good thing actually. So I'm going to go along with that because right. So I just go here. I only need to turn these two lines. The reason why is I actually don't like S written on its own. But I've just got to be careful that when it is done, that all of these S's don't disappear. So for I in range, okay. So this has done nothing other than just use S underscore approximate. It makes it a little bit clearer, to be fair. Calculate the exact solution. Right, I see, okay, so it explicitly has to calculate the exact solution, whereas before, I guess... Has it seen more of my code? Oh no, it hasn't, but because it's almost like it's preempted this piece down the bottom. But I didn't put that in. Or did I? Can't see. No, that was that bit. Okay. Let's go along with it then. Calculate the exact. Okay. Let's see, we'll give it a go. So that was calculate the exact solution, which we did, and then so I'm copying this, and this is the replacement. I'm not sure if I like this or not as much now, to be fair, but let's see. Create the approximate trace, the equivalent to B0, okay. Then create the exact trace, okay, that's equivalent to G before, which is the green thing, I think, yeah, color equals green. So it's done that. Create the figure in traces, okay. Just try and run it then. F5. Launching. Hanging. Right, I've had this before. Hit the stop. Right. So I'm just going to put the comment. Does not I could go back to an original Plotly thing. Right. Fig.write HTML basically, my plot page. If you must open a browser from Python, you can use the, okay, let's just have a look anyway. I should just comment that one out. Right, so it's going to have written it to the to an HTML file. My underscore plot, so now I've got to just search for that, which is here. Revealing File Explorer, and then so that's going to basically be here, and double click on this. Yay! So it does work, and the advantage is that you get this approximate and exact solution for the differential equation. You can do things like zooming in, so there we go. And downloads as a plots. It's going to grab it, move it, reset. Zoom out, zoom in, drag it, zoom in a little bit more, drag it to over there, zoom in a few more times, and then you can just reset it, auto scale. Okay, produce with Plotly, join the vibe. Okay, so that's basically a Plotly version of exactly the same. Yeah, do you like that or not? It swings and roundabouts. You've got advantages and disadvantages. The code is much more verbose now, but I can zoom in. But I actually wanted to have the error messages. But not the error. What sort of like wanted to plot the error. But I wonder where I would plot the error. Because I'd sort of like need to create, like, for example, when this is run. So when this piece is run, maybe I'd want to sort of like have a second chart underneath. So kind of like, if I wanted to get like a chart underneath here that kind of like just sort of like had the error showing, that would be kind of like interesting maybe. But yeah, I think that might sort of like, let me hit the undo button or just the delete thing there. If I was to go back and go to the original and make the error more visible, so I'll do that by making the time steps here. So we can comment out Matplotlib because it doesn't get used. If I was to change this time step back to this 0.1 here, and then do F5 to run it, and then reopen that. So we open the plot, we can see, you know, like the differences are, oops, don't want to do that, Control Z, and I can't do that, okay, So I sort of like to zoom in on like a piece, and oh, that's going to do this. Let's go back again. Right, zoom in to this bit here, panning. So because I can always zoom in like that and then pan, so that's actually a better way of moving around Plotly. But anyway, yeah, we can see. I mean, to be fair, it still takes the same form. It's just visible a lot earlier when you've got the wider time steps. So that's basically it. That's a Plotly version, and the reason why I was going to do Plotly, but I won't do it now, is that I was going to bung all of this into a Streamlit app. So I think that'll be the final piece, which is just to put it in Streamlit. But I won't do it in this session. I'll do it in another session. And yeah, I think that's it pretty much. Yeah, it's done. Oh yeah, just before we go, let's just do this. Right, implement code changes to enhance functionality and improve performance. Well, really, it's Plotly over Matplotlib. So actually, it isn't. So Plotly makes an HTML file that can be inspected, which is a little bit nicer, basically. And yeah, I think we're done. So if you found that useful, whatever, then like, subscribe, follow, all of those things. Go buy the book. Boom. And yeah, we'll leave it at that. I'll bid you a good night and or good day, because you might be watching this at another time. And yeah, like, follow, and subscribe, and do all of the recommendations and all the rest. And